Okay, in this second example, again, you have to find the force in each member of the truss, and then you have to decide the state of each member, whether it is in tension or compression. So looking at this truss structure, there is 1, 2, 3, 4, 5 members, and also there's a 1, 2, 3, 4 joints interconnecting all those truss members. Okay, so in order for us to solve for this kind of problem, we are going to proceed with the method of joints. Okay, the first step in solving using the method of joints is always to draw the support reaction happening at each joint. Okay, so looking at joint A, this is a pin kind of support, so there will be one reaction over here and one force reaction in this direction. And looking at joint C, this is a roller kind of joint, so there will be only one support reaction in the direction of Y, like this. From the previous example, we will start at a joint where there is at least one known force and a maximum of two unknown force. But if you look carefully at the truss structure, there is no such joints which fulfills the criteria that we mentioned earlier. For example, if you look at joint B, although there is one known force of the 3 kilonewton directed on the positive x direction, but then there is a total of 3 unknown force from member AB, member BD, and member BC. The maximum allowable unknown force for us to solve for this kind of problem is only 2. So we cannot proceed with that one. So the alternative in solving for this kind of problem is for us to find the magnitude of each support reaction first. Okay, then only we can proceed analyzing each of the joints. Okay, now for us to find the magnitude of the support reaction for each joint, we assume the whole truss structure as a single unit lah. So again, we apply the equilibrium condition in this particular truss structure. So assuming the rightward direction as positive and summation of all the forces in X should be 0. So that is one force over here, which is 3 kilonewton. The magnitude is positive. And then there is also one unknown force over here, which is positive AX. Okay, so ada lagi tak forces in the x direction? Kalau tak ada, then that's it. Then the total of these two forces would sum up to 0. So solving for this equation, you will get the magnitude of AX to be negative 3 kilonewton. So negative indicate that the magnitude of AX is 3 kilonewton towards the left direction. Okay, now if you are to apply the equilibrium condition in the y direction pula, you can't really solve it because there are two unknowns, which is the AY and also the CY. So in this case, we are going to proceed applying the equilibrium condition for moment. Okay, so from the previous lecture, we will choose a point where there are the most number of forces exist. Okay, so compared with joint A, joint B and joint C, joint A yang ada paling banyak forces acting on it kan. So I'm going to apply the equilibrium condition for moment at point A. So assuming counterclockwise is positive, summation of moment at point A should be equivalent to 0. Okay, so recall the formula for moment is force multiplied with distance, FD. Okay, let us first find the moment caused by this 3 kilonewton. Okay, so the force is 3 kilonewton and the perpendicular distance from the line of force to the joint A is 2 meter. Okay, so we multiply 3 kilonewton with 2 meter. The magnitude of this moment, it is directed in a clockwise manner. So the magnitude would be a negative value. Okay, that's done. Now let us calculate the moment caused by this force Cy. So Cy and the perpendicular distance from Cy to the rotation point A is 2 plus 2 meter, it will be 4 meter. And the direction of this moment is in a counterclockwise direction. So counterclockwise, it will be a positive magnitude. So the summation of all these values should be equivalent to 0. Okay, as there is only one unknown in this equation, which is Cy, we can easily solve for Cy, and the magnitude of the Cy would be positive 1.5 kilonewton. So if it's positive, it means that our assumed direction is correct, which is in upward direction. And now finally, we can apply the equilibrium condition in the y direction pula. Okay, so summation of all the forces in the y direction should be equivalent to 0. There's one y direction force over here, which is AY, and it is positive because we assume it to be upward direction. And the CY we already calculated earlier to be 1.5 kilonewton, and it's positive because it's pointed upward. Okay, and as there is no other forces acting in the y direction, then we can sum up these two expressions to 0. So you can simply solve AY to be negative 1.5 kilonewton. So the negative indicates that the magnitude of AY is 1.5 kilonewton, but it is opposite to the initial direction that you assumed earlier, which is the actual direction of AY should be downward direction. Okay, so now that we have attained all the external forces or the support reaction forces happening at each joint, by which this AY is 1.5 kilonewton pointed downwards and the CY is 1.5 kilonewton pointed upward, and finally the AX is 3 kilonewton, and don't forget that it is pointed to the left. Now that we know the magnitude and the direction of each external forces at the support reaction area, then only we can proceed this analysis by using the method of joints. Again, where do we start? Look at a joint where there is at least one known force and a maximum of only two unknown force. So in this case, if you look particularly at joint C, now the force, the CY is known, which is 1.5 kilonewton going upward, and there are two unknown forces caused by the truss member of BC and also DC. Okay, now similar with the previous example, we are going to draw the free body diagram, particularly at joint C. So if this is your joint C and there is one force acting in the y direction, we call it CY, and the magnitude is known, which is 1.5 kilonewton pointed upwards. And then there is one internal force between joint C and also truss member CD. So let's just assume the direction to be this way. And we are going to call this internal force as FCD. And finally, there is one unknown force between joint C and truss member CB. So let's just assume the direction to be this way, and we are going to call that internal force as FCB. Okay, looking back at the given truss structure, we know that the angle over here is 30 degrees and the angle over here is 45 degrees. So by right, the remaining angle over here is 90 minus 30 minus 45. So there is 15 degree remains over here. In order to simplify our equilibrium condition analysis, so let's just resolve the sangat-bangat punya force into a respective x and y direction. So this FCD can be resolved into x direction with the magnitude of FCD cos 30 degrees, and it can also be resolved in the y direction, by which the magnitude would be FCD sin 30. Okay. Accordingly, the force over here can also be resolved into x and y direction. So we know that the angle over here is 45 degree, 30 plus 15. And if it is resolved into the x direction, it will become an equivalent FCB cos 45 degree. And it can also be resolved in the y direction with a magnitude of FCB sin 45 degree. Okay, now we have translated all the forces into an equivalent x and y magnitude, so we can apply equilibrium condition. So assuming rightward direction as positive, summation of all the forces in x should be equivalent to 0. Okay, so there is one force over here which is FCD cos 30, and it is negative because it's pointed to the left, and there's another force in the x direction of FCB cos 45 degree. So the summation of these two forces should be equivalent to 0. So we can't really solve this particular equation yet because there are two unknowns. So let us just proceed to apply the equilibrium condition in the y direction pula. Along the y direction, there is one force over here with a magnitude of 1.5 kilonewton, and then there's another force over here which is FCD sin 30. It's positive because it's pointed upward. And finally, there is one force over here which is negative FCB sin 45. Okay, so now that is all the expression in the y direction. So the summation of all these three items should be equivalent to 0. Okay, now we can rearrange this equation so that all the unknowns are positioned on the left side and the known magnitude are positioned at the right side. And this would become our second simultaneous equation. Okay, as being taught earlier, you can simply solve for simultaneous equation like this using calculator. So your A1 would be negative cos 30, B1 would be cos 45, and your C1 would be 0, whereas your A2 would be sin 30, B2 is negative sin 45, and C2 is negative 1.5. So you just key in all that magnitudes into your calculator, and you will get the corresponding magnitude for FCD to be 4.0981 kilonewton. Accordingly, the magnitude of FCB would be 5.0191 kilonewton. As the magnitude of both internal force is positive, it means that our assumed direction is correct lah. Okay, so if we are to draw the free body diagram at joint C, this is the direction of FCD. So the corresponding force at one end of member CD will be in this direction, which is the opposite direction to the FCD that we get, and at the other end it will be in the opposite direction as well to ensure the equilibrium condition. So based from this figure, you can see that member CD would be in a tension state. Accordingly, if you want to check the condition of member CB, so the magnitude that we get is positive, it means that our initial assumption of FCB is correct, which is in this direction. So if this is our CB member, then the direction at one end would be like this, which is the opposite to FCB that we get, and at the other end would be like this, which is opposite to one end of it to ensure equilibrium. So as you can see, the two forces are compressing the CB member. So the CB member is in a compression state. Okay, cantik. Now you can proceed your analysis by considering other joints pula. So for example, if we look at joint D in particular, the force at member CD is already known, but the force at member BD and also AD is unknown. So it fulfills the criteria on analyzing using the method of joints. So you can proceed your further calculation or further analysis at joint D pula. So I am going to fast forward this particular part. So you just apply the same technique as being demonstrated earlier. So the first place, you just draw the free body diagram at joint D, and then you draw all the corresponding forces acting at joint D, and then you apply the equilibrium condition, and you try to solve this free body diagram on your own. Okay, you should get the force at member DA to be 4.0981 kilonewton, and it is in a tension state. And force at member DB is also 4.0981 kilonewton, and it is also in a tension state. Okay, looking back to our truss structure, there is only one unknown force at member AB. So it's up to you whether you want to proceed the analysis at joint A or joint B. So if I were to proceed my analysis at joint A, I'm going to draw the free body diagram at that particular joint, and then similarly apply the equilibrium condition. Try this on your own. Okay, if your jalan kerja is betul, then you will get the force at member AB to be 0.7765 kilonewton, and it is in a compression state. Okay, dah siap. Okay, the next thing you can do is you can refine the drawing of all the forces acting on the truss structure. Okay, so that's joint A connecting to joint D, and then joint D connecting to joint C. The joint D is connected to joint B, and then B is connected to C, and also it is connected to A. Okay, the sketching of the truss structure is complete. Okay, now we know there is an external force at joint C with the magnitude of 1.5 kilonewton pointed upward, and there's also an external force at joint A with 1.5 kilonewton magnitude pointed downward, and the AX is pointed to the left with the magnitude of 3 kilonewton, and at joint B, there's 3 kilonewton acting on the positive X direction. Now let us roughly draw the truss members between each joints. I'm going to use this blue marker and fill up with hatches like this. Okay, looks neat and smart. So now I'm going to draw the internal forces between the members and also the joints. Okay, so there is one internal force over here in this direction. Magnitude is 4.0981 kilonewton. And then there's an internal force over here with a magnitude of 5.0191 kilonewton, and so on and so forth. Okay. Finally, we can put a remark on the state of each trust member. Okay, for example, this particular trust member is in a tension state, and then if you look at this trust member, it is also in tension state. And then the trust member between A and B, it is in a compression state, and the trust member between B and D, it is in a tension state, and finally the trust member between joint B and C is in a compression state. Okay, that's here.